intro. Yes, I do fly model helicopters in all 8 directions, also upside down. All right, so normally when I stand on stage, I talk about data plane networking, fast packet transfer, and things like that. This time I'm going to talk about something different, something I've never really spoken of before, so you'll see me probably stumble a little bit out of my comfort zone. But I have 2 questions to start. Hopefully one is easy and one might be more difficult. Who here knows what TLS is, or perhaps SSL? And I'm seeing 1/3 of the people, 1/3 perhaps asleep and 1/3 not knowing it perhaps. Okay, so who knows what certificate transparency is? Because that's what this talk is about. It's very esoteric. I see like 2 people, one of whom I just explained it the day before yesterday. Okay. So first, a little bit about me. I'm Pim. I'm Dutch. I sound American, but I'm not. I'm a member of the RIPE community up north since 1999. My first RIPE meeting was RIPE number 34. You can reach me in my Dutch email address, pim@ipng.nl, and also ch, since I live in Switzerland. In the pandemic, I got bored, so I incorporated IPNG into a small company, and we do these DPDK and VPP routers. You'll see me talk about those a lot. I'll skip the rest because it's not super relevant to this talk. So what is certificate transparency? When you ask for an SSL certificate for your web server or for your mail server, some certificate authority will sign you a certificate saying that that thing belongs to you. This may be news to newcomers to the industry, but we used to not have this stuff. We used to telnet to our routers, and we used to use HTTP without any security for decades and decades. And what was actually a surprise to me as I was creating this slide deck is only 11 years ago, on the left-hand side of this graph, Chrome, the Google web browser, measured less than 40% of secured website usage within Chrome. And this is in 2015, so that's 11 years ago. But if you look at the ramp up, today it's actually almost complete. There are some countries that don't have it on all properties or all websites, but actually most of the lines converge, at roughly 100% of websites being secure. And we have mainly one entity to thank for that. It's Let's Encrypt. They decided to give out free certificates, whereas before you would go to a certificate authority and they would say, well, for the privilege of us proving you're you must pay $200 per year. And it made certificates actually out of reach for many smaller companies. So they just didn't bother. But as is always the case, as these things ramp up, shady enterprises and criminals figure out ways to leverage or abuse such a system. So the root problem is these trusted certificate authorities that we were told they are like gods and you must trust what they say are actually not very trustable at all. Even the very big ones like DigiCert or Google. And so we have seen rogue certificates issued without the owner of the domain even being aware. We have seen misuse certificates by means of configuration errors in these CAs. We've also seen CAs penetrated and taken over by third parties to mint or create certificates on behalf of other users. Sometimes CAs backdate certificates or hide them for whatever reason. And there's basically no accountability for these rogue or incompetent or buggy certificate authorities. So the main takeaway is, as much as we love them, we can't trust CAs as much as they would like us to believe. And although the lining here is not perfectly aligned, I listed 6, and you can see 4 of them here, incidents in not too long ago times where these things actually went wrong. So in 2011, again, HTTPS was maybe 40 or 50% back then, or less than 40%. A CA called Komodo accidentally issued 10 fraudulent certs. The one that got me interested in this whole problem space is DigiNotar, which was a Dutch state-owned notary CA, issued 100 fraudulent certs, one of them for Google in Iran, and a state actor used those to place a man-in-the-middle attack and assassinate state dissidents in Iran. That is a very bad cross to bear if you're a CA and you ended up minting certs that were completely fraudulent. Turk Trust in Turkey accidentally created an intermediary certificate that could sign anything in the world, and they used that for like 6 months until they got found. And then MSC Holding, it gets worse over time. In 2015, issued, I think, 30,000 fraudulent certs. Anyway, the list goes on. So the problem is we can't really trust these CAs. So Google decided to do something about that. So Google owns Chrome, which is very useful, and they have a CA. Not many people know this, but because they got tired of having fraudulent certs on Google properties, they decided to create their own certificate authority, which they use only for their products. Most of these hyperscalers will have one of these as well. So how to create this transparency? We do 5 steps. So step number 1 is provide some form of infrastructure where we can log in a public fashion all of these certificates. And then number 2, sign these certificates by a party other than the CA. So a third party looks at the certificate and says, all right, this one is legit. I'm going to set my signature on it as well and log that publicly. And then number 3, user agents, commonly known as browsers, will check for these time-stamped signatures from the third party. And if they are not there, issue some form of privacy error. So their certificate is somehow valid only if more than one third party validate the CA's work. And you would say, why would a CA care? Well, because the browsers are actually checking them. If you take Safari and you take Internet Explorer and you take Chrome and you take Firefox, you have captured 90% of web traffic. And if those user agents decide we're going to enforce the existence of these extra signatures, the CA's hands are tied, like they have to participate. So these CAs are now incentivized to use these logs. And domain owners can now just look at these logs, which are public resources, to see their certs in the log. When was it issued? And if it was them, they're like, good, I remember that was me. And if it was not them, they're like, what happened? Why is there a cert here that I did not ask for? And so the benefits really are the domain owners. They can find incorrect certificates, obviously also correct ones, but that's less exciting. And CAs can now be held accountable for their operations. Assuming that makes rough sense, I wanted to thank Phil Bonneff from Google, who has this beautiful slide deck previously that I stole the iconography from. There are 7 roles, 7 actors in this ecosystem, and I'll go over them maybe one by one. So the first one is us, the domain owners. Like you own your website, ipng.ch, or nog.net.za, and so on, or google.com. And then there's the certificate authorities. These are the folks who write these certificates. Like this can be Let's Encrypt, or DigiCert, or Sec2Go, GlobalSign, GoDaddy. Like there's many of them, a couple, maybe 100. Then there's the user agents, the browsers, Safari, Chrome, Firefox, Edge, and so on. Then there's the log operators, who are the folks who have this public log that the CAs are meant to write into. And there's a bunch of them. Cloudflare runs one, Let's Encrypt, Sec2Go, TrustAsia, DigiCert, Geomis, and then the one in the circle there is me, IPNG. And then there's log monitors who are just looking at these logs and sort of tailing them to see what is being written to them. Facebook runs one of these. There's a website that's almost always down called cert.sh. Google runs one, SearchStream, Census. Most of the time you can use these tools to inspect the logs, to take a look at them. A specific type of role here are log verifiers. And these log verifiers are looking at the logs to make sure 2 properties hold. A log entry that is written is never changed and never deleted, which is a form of change. So as soon as it's in this public ledger, it can never be changed again, or that's a bug. That's a huge issue. And then there's researchers, folks that are just looking at this and sort of trying to get some intelligence out of the whole log stream and all the certificates set. So roughly 160, 170 new certificates are made every second across the world. And so all of these end up in these public logs, right, by now. So I'm going to give 4 different scenarios on how these actors sort of interact with one another. So the first one here is the domain owner at the left side says, hey, can I have this certificate for my website? And they ask the CA this, say Let's Encrypt. And before Let's Encrypt gives the cert, they will ask the log operator, hey, please log this cert. I'm intending to write one for ipng.ch. Please log it. And then the log operator says, cool, I logged it. And here is the proof of receipt. That is this signature that I signed. Then on step number 4, you get your cert, ipng.ch, which is now the actual cert, including that receipt. And as well, the CA will ask the log operator to log the actual cert. So there's 2 log operations. One is the intent to give out a certificate, and then the second one is the actual certificate. And they're almost identical with a couple of small sort of technical details between them. So interaction number 2, this is users on the internet. Someone wants to watch Nyan Cat, so they go to YouTube and they ask for that Nyan Cat video. And when they connect to the youtube.com or YouTube property, we are asked to prove the identity of that domain. So this is how TLS and SSL certificate validation works in general. This should be quite normal, although it's maybe a different way of looking at it. So the web browser will ask the domain owner in a way like, hey, prove that you're you. And the way that proof is handled is the website owner will give the cert. It's like, hey, so the CA told me, right, that they trust that I am me, and therefore you can trust that I am me because everyone trusts CAs. Except now, you're also giving this signature, this extra receipt that we got previously, right? So when the CA asked the log operator to sign off on the pre-cert and the cert, that signature goes along with the TLS certificate inside of the browser. So in other words, you can see both that the CA gave ipng.ch a certificate, but also that one of these log operators or multiple of these log operators agreed with that operation. So assuming that looks good, we can go crazy on the Nyan Cat video. In the meanwhile, in the background, as these pre-certs and certs are logged into this system, there is this log verifier who asserts there can never be changes once it's in the log, and there can never be deletions of anything that is ever written to the log. And if you're interested in the maths behind this, this is done with a Merkle tree, where every little bit of data gets a signature on it, and then as the data grows, you sign the whole block, and then move on to a next level, and then sign those blocks. And so there's like this string of signatures that goes all the way to the root of the tree. And if any piece of the data in the tree is ever changed, all of those signatures become invalid. So it's really easy to see if anything changed in the meantime. If the log operator wanted to manipulate any certificate, they could absolutely do that because they own the disk for that, right? So they can write something different, but the Merkle tree proof will then fail. Therefore, the certificates will all become invalidated, and the log is then corrupt and has to be deleted and will not be trusted by any browser anymore. So it's an important role that these log verifiers run. And then log monitors. If you know the computer program tail, to like tail a log file, imagine doing that on this log. So you'll see all these certificates as they come in, about 150 per second, and you get to inspect them, you get to look at each certificate as they are written to the log, you get to filter them perhaps for the ones that you're interested in, like your own domains, and you'll see every time any one of these logs gets a certificate request for or a full certificate for ipng.ch, for example. And have yourself be emailed, or assume that if it is not your request that something is wrong, and go complain. So those are the 4 main properties of this ecosystem. So I wanted to show you how you could, if you were interested, participate in this ecosystem. So operating these, there are 2 pieces of open source that you might use. There's multiple types of static log implementations, but the 2 main ones that I'll talk about today are Sunlight at the top here, which was written by a character called Filippo Valzorda for Let's Encrypt. His company is Geomis, And I've linked here sites and the blog and the launch announcements and things like that. I've also written a little bit about Sunlight on my own blog if you're interested in taking a look. So Sunlight is open source. It's on GitHub. You can just download it. It's written in Go. You can compile it and run a log for yourself. Google has been writing log software for a long time. They have a Tessera library, which is a Merkle tree library where you can just add stuff at the tail and it gets signed. And then they have a Tessera CT, certificate transparency, called Tesseract, which is based off of that library, written by Philippe Bonnef and Al Cutter and Roger Nung at Google. A super cool team called the Trust and Safety in Google. So I also wrote a little bit about that, but I'll skip over that. So if you're interested in the hardware parts, this runs on pretty much commodity hardware. It used to be the case that if you ran a transparency log, you would need like a whole data center's worth of compute, like 1,000 nodes and databases and Kubernetes and like all of that stuff. No longer true. You can run on a single computer. So with these static CT logs, you're actually just writing little bits of information in these tiles, these little blocks of 256 certificates into the disk and then signing them with a hash, putting them in the Merkle tree. And you can do this actually at very affordable compute costs. So what I put here is 64 gigs of ECC RAM. By the way, it must be ECC. Imagine a bit flip somewhere writing a Merkle tree hash that is invalid. Your log is immediately like wasted. Like it will never be usable again. You cannot correct from this because you can never change what you wrote after you wrote it. Which also means you probably want good storage. So maybe no Samsung QVO 4 terabyte on sale. I use these Kioxia or Toshiba NVMe platters and these SAS3 Samsung that used to be in NetApps, right? NetApp shipped those. So these are not cheap, unfortunately, especially now with SSD crunch. But very important to have good disk, performant good disk, because you can never lose data. That's the whole purpose of the log, is to never lose it. CPU-wise, 16 cores would be enough. We run about 12 CPU seconds per second at peak. And so if you had 16 CPUs, you would be good. And a 10 gig NIC is called for 1.8 gigs. Interestingly, just yesterday, this turned more into like 3 gigs because someone in this audience started scraping my logs. And then it's hypervisor friendly. So if you used Proxmox or Zen or QEMU, KVM, you can totally run this on hypervisors. That is what we run them at IPNG as well. But please be careful with ZFS and hypervisors. You definitely want to pass through the disks to the guest so that it can do ZFS for itself. Otherwise, you're just asking for trouble. So hardware-wise, this computer is not super expensive. Except perhaps for the NVMe disks that can run up a cost. So to build these now, we create a ZFS pool. We use RAID Z2, which means there are 2 parity disks for your pool. We have 4 disks in total, which means half of our disk is for parity and the other half is for storage. I put the command line here because there's some issues with performance and with like throughput, especially the A shift if you've ever used ZFS. Setting on auto trim so that your disks don't write themselves into oblivion after a while. For Hendrik there, setting up the X attributes so that you don't get stuck on this stuff, and then just adding the 4 disks. The key material of my log, the ones that I use to set signatures on the requests that I get from Let's Encrypt and Google and Sectigo, is obviously very high IP. Like that is steel-worthy stuff. And so we put that on an encrypted volume, which we mount and decrypt only at start time and then unmount again so that the keys are in memory of the serving process, but if the power were to ever fail or the machine were to get stolen, the keys at least are safe. So the second line here is creating a data set called ENC for encrypted, where we keep all the key material and configs. And then we'll create a data set called logs, in which we will create one log called Rennet and one log called Gouda, which are cheeses. Each log operator chooses their own mythology, I guess. I chose cheeses because I'm Dutch. And Rennet is an ingredient for cheese. Yes? And Gouda is obviously the famous Dutch cheese. And then for each half year, we'll create a log shard. So this started in 2025 H2, and then all the way through to 2027 H2. And as time goes on, we will just create new log shards as the old ones fill up. We'll set quota on them, about 2 terabytes for each half year. And if you recall, there was 7.68 terabytes of usable storage in the pool, which means we should be able to keep 4 of these at any given time on disk. And there's only 2 at any given time that are typically written to. All right, so now we have our ZFS stuff and our encrypted file system. We can now create the Sunlight configuration directory and edit in a file called sunlightstaging.yaml. So this thing is actually pretty simple, and I really appreciate this in Sunlight a lot compared to the alternative that I'll show in a second. The config file says, let's go listen on all addresses, IPv4 and IPv6 on this port 16420. And then I'll write my checkpoints in this file over here. And then my log has this long list of attributes, like a name, when we created it, which is called the inception, how often we write the signed tree head, how many certs per bulk transaction do we accept, which is 1,050 in my case, which URL can we use to write to the log, which is called the submission prefix, and which URL can we use to read from the log, which is called the monitoring prefix. The field under that is the CCADB. So this is the common, I think, CA database that Mozilla maintains. So all of the roots that you may have in your web browser on your OS, they're somehow listed right on this central website, which Mozilla maintains, and it's called the CCADB. And they have trusted and testing roots. And so for a production log, we'll use the trusted ones. And then we have some extra roots that we also wish to trust. Maybe I should tell you, when you submit to this log, not everyone can do that. So if you were to start posting to this log right now, it'll be rejected because the signatures of the CA need to be present. And the only people who can make those signatures are the CAs themselves. So the idea here is this is a public open endpoint on the internet, but the only people who can write to it are people that have a certificate that is in this root list. And then the last two, I'll skip over the directories, those are kind of boring. The last two are this temporal shard starts in 2026, January 1st, and ends 2026, July 1st. So that means any certificate with a transpiry date within that window is eligible to be written to this shard. Which means if you wanted to write a 2028 certificate to this shard, it would be rejected. You need to write it to the 2028 log shard instead. So that means all the certificates that end up in this particular shard will be those that have an expiry date in that window. All right, so then if I have the write path, Sunlight also has a thing called Skylight, and Skylight is a companion, and it's the read path. So it has a much shorter configuration file. In fact, this is the whole thing. A port, and then what is the monitoring prefix, and what is the directory to go serve this data out of. Think of it like an Nginx, but with very specific opinionated configs, like which accepted encoding types, and which ones are zipped, and which ones are not, and which ones are cacheable, and which ones are not. So what I appreciate about Skylight is it sets this all up for you. You don't have to think about all of the config. By the way, I did have to think about all the config. I'll get back to that in a second. So then you start the Sunlight job for the write path, and you start the Skylight job for the read path, and you're off to the races. Your log is running. So that's Sunlight. And then Tesseract is a different implementation. And I felt back then when I started that I may as well use both types. So run 2 logs, one on Sunlight and one on Tesseract. And I think I'll go over this one a little bit faster. It's very similar in a way. It has this Tesseract YAML file that describes your logs. And I made it look very similar to the ones in Sunlight. Unfortunately, Tesseract does not come with the user experience that Sunlight comes with. Tesseract is only a binary that you can compile, and it has no configuration harness. So I wrote one of these called the external tool for configs here, Tesseract genconf, which will read this YAML file and then generate a key, generate some HTML files, some environment variables for the jobs to run in, some Nginx for the read path, and then some roots because it did not used to support CCADB. It does not come with a read path. So the main struggle I had starting all of this is you start writing all the stuff to the logs and you point some Nginx at it, and everyone started screaming at me that my read path was broken because I didn't set the proper caching variables and I didn't set the proper encoding types, and I must have gzipped this one but cannot gzip that one, and this one must be JSON, and so it was a little bit of an annoyance to me. And eventually, after 5 rounds of being yelled at by the community, I ended up with this gen Nginx, which will generate the whole Nginx configuration with all of the bells and whistles all set up. All right, so here too, I'll look at one of these .env files, and if you run stuff in Docker, this should not be foreign to you. It's just a bunch of arguments that I'll put, and then I'll start the Tesseract, and I'll link in this auto-generated Nginx config file for lipase 2026 H1. Lipase is one of the ingredients that goes into cheese, and one of our operators is Greek, and so the Tesseract logs are called halloumi. So performance-wise, the guys at Google wrote a pretty cool tool called the Hammer. That is MC Hammer in the bottom there. And Hammer just load tests your static log. And I load tested them side by side on the same hardware. Sunlight does about 6,500 to 8,000 certificates per second. And as I said, the current rate in the internet is about 160 or 170. Tesseract goes way further than that, does about 20 to 22,000, and gets served out of Nginx. So to wrap up, the pros for Sunlight is it has this built-in read path with Skylight, very good YAML config. Has a little bit more mileage because it's a little bit older. And in fact, Tesseract had a very gnarly bug that bricked one of my logs as well as one of Google's logs. But otherwise, Tesseract is much faster. It's more efficient. It runs on AWS and GCP if you were to run it on a cloud. So one thing that I should note is the reason why IPNG and Geomis were eventually asked to run one of these is because the industry itself started getting a little bit antsy that all of these logs were from American companies on hyperscalers. So they were either at AWS or they were at Azure or they were at GCP, and they were operated by American companies, and folks kind of said, maybe we want some indie independent log operators that are not on cloud and just run this stuff in their own premises, in their own data center. So they're actually quite keen on small operators. Don't be worried if you were to be interested thinking, that's not for me, that's out of my league, these are the Google people. They actually maybe prefer the smaller operators. So we did have to learn a bunch. It's not free, it's very esoteric, and there's not a huge documentation corpus online. But there is a Slack channel, which is really cool, and there's smart operators there, monitors, developers, the folks who wrote this code. The other thing that I'll note is we got DOSed up the wazoo with this thing when we launched. We got Tor posting certificates or reading certificates from another log and then cross-posting them to our log for reasons unclear to anyone in this community. And you should budget some time and some capacity for this. So you can't just run it and then forget about it and turn it off. They require a 99% uptime on a 30-day rolling average, and Google will berate you and remove you if you end up violating that without a good reason. All right, so the results are these 2 logs that you can go look at. Renette is our Sunlight staging log, and Lipase is our Tesseract staging log. And then the next slide, again, horrible alignment. But a bunch of links that you can see. The certificate transparency homepage originally started by Google. The specification for static CT, and one thing that I really appreciate from these folks is they're not too interested in going through the IETF song and dance because it's very expensive and time-consuming, so they just have a GitHub page where they're like, this is the spec, and we all agreed. That's good. It's like IETF underdog. And then Sunlight and Tesseract, the 2 main implementations. There's a bunch of Go clients. There's a bunch of extra stuff that you can look at. The C tool is maybe one point worth pointing out. It's a little program in Go that allows you to look at the read path for these logs, any one of these logs, to just get certificates back out on the other side. And then there's some mailing lists that unfortunately got chopped off due to the formatting. But if you're interested in any of this stuff, come find me. The community is like super, super friendly. You don't have to be a crypto nerd. In fact, I am not. I'm a data plane guy to participate in it. And then I got 20 seconds left and a video of 33 seconds. So let's see if that fits. Gouda in the wild. And it's a video, and I'm hoping that AV can help run it. All right, so we're here on the Indico for this event. And by pure happenstance, when I go and view the certificate, this is in Firefox, I can see that this is for events.inks.net.za, and it was issued by Let's Encrypt, and it was issued here at 4 a.m. GMT on Friday the 27th of March. You may have seen these before. And if you scroll all the way down to this page, you'll see these SCTs have two signatures from two different log operators, Sectigo, by a log called Elephant, and IPNG Networks by a log called Gouda. So I have validated that Let's Encrypt was entitled to give events.inks.net.za the certificate, and without that, you would not be able to visit the website. That's it. That's what I got.
Can I ask a quick question?
Yes.
Ed from Zenog. Two ones, actually, probably. Other than feeling good and fuzzy, what would the motivation for anyone in this room be to host a log up, well, a log like this? The second question would be, do I understand it right that the logs don't necessarily have to be complete, because obviously you mentioned the 99% uptime, so they'll probably miss something every now and then, but it'll still be useful if it's not complete?
I'll do the second one first. Instead of demanding that log operators have very high uptime, the CAs stripe over 5 different logs. So they will write to 5 different logs and take the first 2 that gave an SCT back. Which means that if mine is down, I just can't participate in signing the pre-cert. But maybe Geomis can, or maybe Google can, or maybe one of the others will. And there are currently 7 or 8 logs, I think. And so as long as enough of them are around. So for example, if AWS and GCP were to have a simultaneous outage, like many of the very large log operators just fall off the planet, and people crowd on the smaller guys. And then your first question, who cares? Like, why would you do this? There are these things, I guess, that maybe it's just me, like the internet needs to be safe and people need to see to it that it is. It's perhaps not the most glamorous job to run a log like this, or a CA for that matter. But I think those who believe in participating and helping out the bottommost layer of critical infrastructure on the planet may find participating in this type of a community an interesting investment of their time. So I do it for the love. Jaco.
Jaco here. The log operators, how do they determine whether a specific CA is actually permitted or allowed to issue a certificate for a specific domain?
Yes, good question, and that's this CCADB. So HCA is actually permitted to sign any domain in principle. They are called a root CA for that purpose. And Mozilla has this list of root CAs. And each operator, sorry, I shouldn't say operator, each user, like OS maintainer, each CA, each log operator, each browser manufacturer gets to decide for themselves what are the CAs that I trust. So for example, sometimes people went way in the wrong in CA land, and Google Chrome would kick out the CA and make them untrusted. That's a very big deal for the internet because it means that every domain that was minted by that CA in Chrome would just stop working. Safari has done this also. Like you can look on the internet a couple of really big events where a CA really went in the wrong and they essentially got banned. So how do you do that? Well, I don't do it myself. I just use the CCADB as is given by Mozilla. And then every quarter I inspect the diff, like CAs that come in and come out. And the agreement we have as log operators is that once we accept the root CA, we will never remove it again in that log shard. So essentially that just keeps on growing. That list keeps on growing. Thank you for the question.
Hendrik Versage, Envisage Cloud Solutions. I'm the guilty. One of the interesting things that I've picked up with certificates getting issued is that as soon as you get a certificate for any name, basically, that site gets sort of targeted. Is this something that these CT logs assist in making available for these sort of scrapers, attackers, or is it something that we need to be aware of? How do you see that happening?
Yeah, well, the answer is yes. Like, these logs absolutely facilitate scrapers finding your website the minute you get a cert for it. And actually, you used this the other day because Hendrik was interested to see who in COSA has SSL or who in COSA has like a proper IPv6 or whatever, but scraping the zone is a little bit difficult because DNSSEC and whatnot, right? So you can just look at all COSA domains coming out of these logs by tailing them. And then you'll find every single one of these domains that requested a certificate, at least if it wants to be usable in any modern browser, which is literally everyone, right? So there are people who are tailing these logs, find new domains that they haven't seen before, and immediately engage in like cold call sales and other stuff. And that is unfortunately an attribute of radical transparency. Like, if you're transparent about all of these certificates, then yes, you put them all in a public ledger that people could read.
Thank you so much, Pim.
Oh, thank you, Portia.
Please let's give him a round of applause.
Cheers.
Okay, for the next presentation,